Okay, so let us start. Yeah. So what do we do today? So I'll continue this propositional. Okay, yeah. So happy Pongal, happy Sankranti to everyone. And on this auspicious occasion, let us try to learn propositional logic and be happy about it. Okay. So yeah, I see a few chats about happy Pongal. Yeah. So let's get back to propositional logic, please. Okay. So yeah, so what we will do is we will look at what are these, and I'm sorry for making you come and sit here on a on a holiday. Sorry about this because we have missed some lectures and I don't want to bunk this class. Okay, I hope it will be worth it. Okay, so let's see. Yeah, so we want to look at this notion of sequence. Okay, we did that in the first lecture on logic, but it was not very clear. Let's revisit that sequence. So let's start with this example that we did last time about this logic puzzle that four siblings go shopping with their father, some blah, 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 and prove that this. Okay. Now, you remember, in order to show this, we were making use of some logical language, and we defined a proposition P to be that Abhay gets shoes, Q to be something, R to be something, and so on. And then this entire question of proving this turns out to be what? I am given that P implies not Q. I am given R implies S. I am given not P or what is this? Or S implies M. And finally, I'm given not M. And I'm asking you to derive the fact that not Q and Arun did not get a t-shirt R. Okay. So this entire example can be written as, it's just a language to write this. So given these premises, derive not Q and R. Okay. So this is an example of a sequent. Okay, so this is one. Oops. Now, what about this question? So what will the sequent be for this question? So instead of saying explain, so is it possible to determine who is chatting? Suppose I had said, prove that A and D are chatting. Okay. Then the sequent corresponding to this question is what? So remember, we wrote A to be the proposition that A is chatting. B, C, D, and E. Okay. And then the premises are A or B. Okay. But yeah, or both. So it's fine. A or B. C or D, but not both. That means what? C or D, and it's not the case that both C and D. So I will not write it, instead I'll just write it like this. I'll write it as two premises, C or D, not of C and D. Okay. And then if E is chatting, C is also chatting. E implies C, C implies E. Okay. D and E are, sorry, D and A are either both chatting. Oh, sorry. This is just E implies C. Okay. D and A are either both chatting or neither is. This is what is D implies A implies D. And finally, if B is chatting, so are A and E. Given these premises, derive A and D. Okay, so this is a sequent corresponding to this question. Okay, now, so what is the sequent for this question? Okay, just write it. I just want to know if you have understood this notion of sequence. Yeah, so what are the premises? So suppose I say A means A is night and B means B is night. That is a proposition, B is night. Okay. Now, what are the premises? What are said? A says B is a knight. From this, what are the things we can infer? If A was a knight, then that implies that B is knight. Okay. Whereas if A was a knave, then this implies B is knave. Okay. Now from the statement that B says, what can we infer? If B is knight, then the two of us are of opposite types. That means not A. Okay. And if B is knave, this implies what? Both of them have to be of the same type, because B is telling a lie. So both of them have to be of the same type. That will imply not A. Okay. And from this, we want to derive not A and not B. So this is so I'm just rephrasing the question as a sequent. If the question was prove that A and B are knaves, given these premises, you can write it symbolically using this sequent. Okay. So have you understood the meaning of sequence? See, this is a bit more abstract way of. So A could be anything. In this case, A is knight. Okay. But this is a more abstract, what do you call, statement. Like, and then this is one instantiation of this particular abstract statement. Okay. So do you understand the notion of sequence? Please type yes if you have understood.
Excuse me, sir.
Yes.
Sir, so all the four statements that we wrote on the left side, that A implies B not A, all of these are the premises that we have inferred from the information given?
Correct.
Okay.
So in the previous questions, it was kind of straightforward. You just had to write directly. In this case, we had to make some
We took the different cases and then we saw what is happening.
yeah, correct.
Okay.
Yeah. Okay. Fine. So now let us stick our mind. Oh, wait, a sequent is the whole expression. This entire thing is called the sequent. Let me, sorry. This entire thing is called a sequent. The LHS is called premises. The LHS side is called premises. Each element in the LHS is called a premise. And then whatever on the right hand side is the conclusion. So in general, a sequent takes the following shape. You have some formulas on the left hand side called premises. And then on the right hand side, you want to derive psi, which is the conclusion. You want to conclude psi given the premises phi 1 till phi n. So in the previous case, you want to conclude this thing given the premises. Okay, so this entire thing is the sequent. Is that fine? Good. So the next question is, so from now, instead of giving a text for the question, like giving a whole story, do this, do this, do this, and then instead I can just give you a sequent. Okay, I give some. So for example, I could have given you just this much. Prove this sequent. Okay. So then how do we go about it? Okay. So here is what we have already seen several sequence in these questions. And how did we prove them? So if you look at the proofs of how we solve those examples, certain things kept recurring. Okay, certain arguments we kept reusing. So for example, we kept reusing this fact. If a P is true and P implies Q is already derived, then we can derive Q. Okay, we made use of this several times in these examples, where P was standing for different things in different examples. Another thing which we were using is suppose we assume P, that is P equal to 1. Okay, so assume P. And then if we arrive at a contradiction, what is a contradiction? We were able to derive some Q as well as not Q. Then our assumption is wrong, which means we should be able to derive not P. This also we did in several occasions. Okay, this is this template we used in several occasions. Another thing which we used was, suppose P is known to be false, we derived P to be false, but P or Q was true, then certainly Q has to be true. Okay, so these are all some examples of of the thought process that happened in most of the examples. Okay, now our goal is, can we come up with a set of rules? So we want to formalize statements like this and make them symbols. Okay, like how we made this entire thing into a symbol, we want to make the entire proof into a symbolic set of statements. Okay, that is what is the goal of natural deduction. So instead of writing a proof using English text, proofs will be a repeated application of certain rules which will look like this. Okay, and we should be able to prove sequence. So this is the main motivation behind natural deduction rules. Okay, so is the motivation clear? Instead of writing English text proofs, we want to write proof, I mean, where we are repeatedly using certain same things, we want to actually formalize them, pinpoint them, and then write it using those particular rules. We will call those rules by names, and then we say that now we apply this rule, now we apply this rule, now we apply this rule, and hence we derive the conclusion. This is what we are going to do. Okay, so clearly, if I have a sequent, so there are logical formulas, phi 1, phi 2, and so on. The formulas have operators, and or not implies. There could also be a bot, which although we have not seen any example yet. Somehow we need a way to replace these rules with, you know, in the final derivation, you can again have these kind of things. Somehow we need rules to work with these symbols. Okay, so that's why what we will do, we will try to give a rule for each operator, how to handle each operator in your proof. Okay, this we did last time, but let me repeat. So here are two rules to handle conjunctions. Okay, so if you have derived in the sequence of your proof, so at some point in your proof you have derived phi and you have derived psi, then you can derive phi and psi. It's a very natural derivation. If you have derived this statement and you have also derived this statement, you can derive the conjunction of the two statements. Okay, the second thing is, how can I eliminate conjunctions? If I know that A is true and B is true, then I can use the fact that just A is true for my later derivation. That is what this thing says. If I know that phi and psi are true, I can derive just phi. Similarly, I can derive just psi. Okay, see, we are every argument that we use needs a symbol now. So that's why we have things like this, which look natural, but they just pinpoint what exactly we are doing. Okay, and we saw an example. So here is a sequent. It looks very, I mean, it looks trivial, but so then what is the proof of this? If I know P and Q, if I know R, these are my premises. I want to derive Q and R. Okay, I mean, for example, I can say Abhay wants shoes, Asha wants necklace, Aditi wants bangles. From this, I should derive Asha wants necklace and Aditi wants bangles, which is kind of immediate. Okay, so let's start with these kind of simple things. So how do you write a proof of this fact? The way we are going to write it is, first we will write the premises methodically. So the first premise is P and Q. The second premise is R. Now I want to derive Q and R. So somehow if I have derived R and if I have derived Q, I can use the AND introduction to derive Q and R. So I need Q. For that, I will use this and I will eliminate P and get Q. So this is the AND elimination rule. If I know phi and psi, I can use phi. If I know phi and psi, I can use psi. So this is the AND elimination on the second component. This is the explanation of how I derived Q. I derived Q by applying the AND elimination rule to the first derivation. Okay. And how do I derive Q and R? I apply the AND introduction rule to R and Q. That is, whatever I derived here and whatever I derived here, I apply the AND introduction. That's all. So this, whatever this box is the proof of this sequence. Okay. Now, so write a proof of this sequence using the AND rules. We have done this, but it's, please try it again. So let's try to give a proof. You just check it if it matches with whatever you have. So first, as a first thing, let me write the premises. P and Q and R is a premise. Secondly, S and T is a premise. See, note that finally we want Q and S. To get Q and S, I need to have derived Q, I need to have derived S, and somehow then I can apply the AND introduction to get Q and S. So now I have to see how do I get Q and how do I get S. Okay, so we just have to do elimination some number of times. So first of all, I apply AND elimination to the first derivation, first thing that I have to get P and Q. Okay, so from P and from P and Q and R, I derive P and Q. Secondly, I once again apply AND elimination, but projected to the second component to whatever I derived now. Now to get S, I apply AND elimination to 2. Okay, and then finally, I get Q and S by applying AND introduction to 4 and 5. So this is the proof for this sequence. Okay.
Sir, are we required to explain what are the actual, the steps are for lambda E1 or lambda E2, for example?
No. This is and E1. Sorry, this is not. This is the name of the rule.
Yeah. I mean, are we supposed to explain what the rule is doing while, like writing the steps here?
Like, see, I have only written which rule I have applied and to which derivation I have applied. And I think this is needed. Okay. Because otherwise it won't be very clear if you just write P and Q. See, in this case, fine. If you have a long derivation and suddenly you write P and Q based on something here, then it will be difficult to know how you derived it. Okay, so that's why it's just important to make it explicit. But it's just I'm just writing the name of the rule that I applied and to which derivation I applied, which to the derivation of the line number 1. This is what I've already derived thanks to the premise, and I applied the AND elimination rule.
Yeah, what I was asking is, do we need to explain what the actual, the work of the rule is?
No. You just write the name of the rule.
Thank you, sir.
Yeah. Okay.
Sir, why the sixth number equation is and I?
This is AND introduction. The name of the rule is AND introduction. See, if I have phi and psi, then I can derive phi and psi. I am applying this rule. So the name of this rule is AND I. Okay. So I applied this AND I rule to this and this. Is that clear?
Okay.
Yeah. So here my Q was phi and S was psi, and I derived phi and psi, essentially. Okay. Good. So let's look at a new rule for a different operator. So what about the implies? So for each operator, we will have an introduction rule and an elimination rule. Okay. So let me start with the elimination rule first. Okay. Suppose I have derived phi and I have also derived phi implies psi, then I can derive psi. See, we have used this thing. If I know P is true and P implies Q is true, then Q is true. We have used this several times in the examples. So the name of this rule, you can write it as, this is the name of the rule, implies elimination. It also has a fancy name called modus ponens. Okay. Now, we also have an AND introduction rule. Sorry, an implies introduction rule. That is what I've written. So this is the name of the rule. I did not mention it clearly. This is the name of the rule. This is the name of the rule. Okay. Now, how do I introduce an implication? Suppose I assume phi, assuming phi, if I'm able to derive psi, then I know that phi implies psi. Okay. So that is what this box means. If you want to do an introduction to implication, you first assume phi. Okay. and then you do all your rules here. And if you're able to derive psi, then below this assumption, you write phi implies psi. Okay, it just means that this thing is derivable. So let's see an example. So I will do this example. So the sequent is, my premises are P implies Q, P implies Q implies R, and from here I want to derive R. Okay, so I have to, maybe I'll just give some time. Just try for a couple of minutes and then I will give you the answer. So I will also copy the two rules here for your reference so that.
Excuse me, sir. Could
Yes.
you read the elimination rule again as to how to
Okay.
say it?
So if I have derived phi and I have also derived phi implies psi, then I can derive psi.
Okay, got it, sir. Thank you.
So let me do it along with you, and then maybe in the next example you can try it out. So first I will mechanically write all the premises. Plus Q plus R. So now I have to get R. Okay. So in order to get R, I have to reach this point somehow. Okay. So what we will do is, first we will use this and this to get just this Q implies R. Okay. And somehow if I'm able to derive Q, then I also have derived R. But then I can derive Q from here. Okay. So let me do it. Okay. First step, I apply the implies elimination to 1 and 2. Okay. I get Q. So P is phi, P implies Q is phi implies psi, and I derive psi, which is Q. Secondly, I apply this elimination rule to 1 and 3. What do I get? Phi, I can get Q implies R. So I get Q implies R by applying the implies elimination on 1 and 3. Okay. Now I have 4 and 5. I can once again apply the elimination rule to get R. I apply the implies elimination to 4 and 5. And I have got my conclusion. So it's just a repeated application and we are just writing it clearly. So this is the proof. So can you say yes if you have understood this, please? because I don't get many answers because it's difficult to write the proof. Okay, good. Excellent. So let's see another example. So try this out, please. So let me do this. Let me again once again copy this. See, clearly we want an introduction. I mean, we need to use the introduction rule. I need to introduce. See, I need to get this, right? So in order to get this, I need to use this rule where phi is P and psi is Q implies R. Okay, maybe I'll write it. Finally, I need P implies Q implies R by using the introduction rule somehow. Okay, and how can I use this introduction rule? I need to assume P, okay, and I need to derive Q implies R. Okay, Now, yeah. Now, how do I get this Q implies R? Because this is yet again an implication. And in order to get this, I need to have assumed, okay, wait, I don't have space. Let me just make it a bit big. So firstly, I want this, and how do I get this? By applying the rule, I need to assume P, and somehow if I have derived Q implies R, then I can derive P implies Q implies R. Now, how do I get Q implies R? I need to have assumed Q somewhere, and I need to have derived Q implies R, so that, sorry, I need to have derived R, then I can say that Q implies R. So I apply this rule on this intermediate part. Okay, now this is the point. But then when I'm here, I have assumed P, I have assumed Q, which means I can derive P and Q. See, I'm giving a rough thing first and then I'll do it properly. But then if I've derived P and Q, then I can use the premise to derive R. Okay. So this is the point. Now let me do it properly. Okay. I will erase this and I will do it a bit more slowly. This is just the way to get to this. So first, I will write the premise. There is a single premise. Okay. Now I need to, what I'll do is I will start. So when I have this kind of a box, it means I'm starting a new assumption. So let me assume P. I'll write it as an assumption. Okay. And inside that, I will start yet another assumption where I'm going to assume Q. Okay. And now, inside the context of this assumption, okay, I can derive P and Q by applying the AND introduction to 2 and 3. Okay, so we are inside this context of the assumption. So in English text, suppose you say assume blah 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 and you're in the same paragraph, something like that. Okay, it's of that, it's like that. Sorry, one second. Okay, I have derived P and Q. Now I can use the premise, the hypothesis that is given, to derive R by applying the implies elimination rule to 1 and 4. Okay. Now I close this assumption. So starting with Q, I have been able to derive R inside this bigger box. So I will write Q implies R and I will close the bigger box. So this comes by using the implies introduction to 3 to 5. So this implies introduction, this is the box. From there I have derived Q implies R. Q is my phi, R is my psi. Okay, and I derived Q implies R. Now once again, I look at this box. Starting from P, I did something, I have derived Q implies R, and then I can use this rule to say that P implies Q implies R by applying the implies introduction to the statements 2 till 6. Okay, so this is a new thing that is different from the and other thing. I mean, different from the and is that we have an assumption and a context around it. Is this part okay? So have you understood this proof?
Can we use AND elimination directly in the LHS part of the sequence?
How would you use AND elimination?
Like eliminate P so that Q implies R.
No, no.
Is
What
it
is
possible?
no? What I mean? How would you read this? First of all, how would you read this formula?
P and Q implies R.
That means the bracket is like this, no?
Yes.
Correct? It's P
Okay.
and Q implies R.
Mm-hmm.
Now, how would you use AND elimination? So, AND elimination should be like phi and psi. I can get phi. What is your phi and psi in this formula?
Okay, okay. Got it.
See, you have to, yeah, you cannot use the rules at some internal level. It should be, this formula should look like phi and psi, and then you can get, yeah. Any other
Okay.
questions?
Sir, I'm unclear at only one place.
Hmm.
The proof I followed, but the entire proof is based on two assumptions that we are making, and nowhere we are trying to prove that, or we are trying to state that these assumptions are correct or they are not correct.
No, no,
So,
no. So what is the meaning of this implication? Phi implies psi means if I assume phi, can I derive psi? Okay. So what is the meaning of P implies Q implies R? If I assume P, can I derive Q implies R?
okay.
Okay. And in order to derive Q implies R, if I assume Q, can I derive R? And in this
Okay.
context, yeah.
Yeah, yeah, my doubt is clear. We don't need to consider if P is false or not, because if
Yeah.
it is false, then it is automatically true and we have just shown that if it is true, then we can derive the
Exactly.
other side of. Okay,
Exactly.
clear,
Yeah.
clear, thanks.
Okay.
So can we directly assume P and Q?
You can do that. Wait. No, no. If you do that, so how will you, I mean, so then you will, how will you proceed? See, finally, I need P implies Q implies R. I need the context of this box. See, if it had been P and Q and I derive R, I will only get P and Q implies R. I will get back the premise. I mean, which is correct, but which will not give what we want.
Yeah, okay.
Any other questions? Okay. So how about trying, here is another example. Try this out, it's the converse. Okay, so let's try to give the proof. So first, let me write this as my premise. So here is where we need to assume P and Q. Yes, indeed, we need to start with the assumption P and Q as suggested for the last thing. But here we want to do that because we want to be able to derive P and Q implies R. So let me make this assumption. Okay, if I make this assumption, then I can derive P by applying AND elimination to 2. I can also derive, I can derive Q by applying AND elimination. This was AND elimination 1, this is AND elimination 2 to the second statement. Now I use my premise and the fact that P has been derived to derive Q implies R. So I can derive Q implies R by applying implies elimination on 1 and 3. Okay. Now I need to eliminate, from Q implies R, I need to get R, but I have luckily derived Q. So I can derive R by applying implies elimination to 5 and 4. And I can close my assumption. And from this, I can derive P and Q implies R by using the implies introduction from 2 to 6. So I'll repeat from 5. See, up to this is fine. So using Q implies R and Q, I can derive R. So that's what I did. I am applying the implies elimination on this and this. Okay. Is that clear? That was a question. Okay. And after doing this, so essentially what I want from P and Q, my goal was to derive R and I'm done. So I'll just close this box to say that P and Q implies R. So this is the proof. Just say yes if you have understood it, so that then I will proceed to the. Okay. So I think we need to see several more examples before you get into the, get into this groove. So let me now give you the last set of rules for today. Okay. So far we have seen rules for AND, we have seen rules for implies. Now I will give a set of rules for OR. So once again, there will be an introduction rule and an elimination rule. Okay. So when can I introduce OR? If I have derived phi, I can always add some extra thing. Because if I have phi or psi, even if one of them is true, phi or psi will be true. So if I've derived phi, then I can just write phi or psi for some arbitrary psi. Okay. Similarly, if I derived psi, once again, it's the same thing, just that we are making a different distinction between whether we are putting it in the first place or not. Okay. So if I've derived psi, I can also derive phi or psi. Okay. This is my introduction. Now, how can I eliminate an OR? Okay. See, if I have a phi or psi, either of them has to be true. Now, if I can show that starting from phi, if I'm able to derive some chi, and starting from psi, if I'm again able to derive chi, it doesn't matter which one of them is true, chi has to be true. Okay. I don't remember whether this chi or xi, it doesn't. Okay. So I have phi or psi. Starting from both of them, I am able to derive this chi. So then I can just derive chi. Okay. So let's see some examples and then it will be clear. Let me copy these rules so that. Yeah, there's a very simple example. Oops, sorry. how do I derive Q or P from P or Q? It looks very, stupid, but we need a proof. So let's say, I'll just write it out here. I have P or Q is premise. See, when we work with symbols, several things can happen like this. Okay, so now I need to derive Q or P. Okay. So what will I do is I will use this rule. Okay. I will assume P and show that I can derive P or Q. I will assume Q and show that I can derive P or Q, and that is enough. From this, this and this, I can derive P or Q. Okay. So I will assume, yeah.
So we want to derive Q or P.
Sorry. Yeah, correct. Yeah. Okay. I will assume P, and then I will apply this this rule. Which rule? This rule. To say I have derived Q or P. This is the OR introduction to 2. Okay. Fine. I close this box. This is my first box. Then I will assume Q, and I can once again derive Q or P. Sorry, this is my assumption. This is, I'm having an OR introduction 1 on 4. Okay. Now I will apply the OR elimination to get Q or P. So where I'm using the OR elimination, I'm applying it on 1. This is my phi or psi, comma 2, 2 to 3, 4 to 5. Okay. So 2 to 3 is my first box, 4 to 5 is my second box, and both have derived Q or P. So this is the proof. Okay. This is just to illustrate how to use OR. Now let's see an actual, maybe some, just check this example. So let me start doing the proof. Let me write the premise. P or Q or R is a premise. So I want to get this thing. Okay. So for this, I need to use an OR introduction to get this. So if I have a way to derive this or this, I'm fine. Okay. And then I need to use an OR elimination to get this. So let me assume P or Q. See, my format will be, I will assume P or Q, and then I will derive P or Q or R. Then I will assume R, and I will derive P or Q or R, and then I will apply this OR elimination to derive this final thing. Okay. So let me first assume this thing. If I assume P or Q, how do I get P or Q or R? So once again, if I have to use the rule, if I have to eliminate the OR rule, so let me assume P. Inside this, I make an assumption. Okay. If I have this, then I can derive this by the OR introduction 1 rule on 3. Okay. Now suppose I assume Q. Okay. Using OR introduction, I get this. So just it's a bit tedious, so just stay with me. I use OR introduction 1 on 5. And if I have this, then I can of course do P or Q or R. Once again, I apply OR introduction 2 on 6. Okay. So now what? So now I close this assumption. Okay. So from P or Q, I have derived. Sorry, I have to put one more thing and then. So now I can derive P or Q or R based on the OR elimination applied to 2, 3 to 4, 5 to 7. Okay, so then I close this first assumption. So since I don't have space, I will continue here. 9 will be, I start with R as an assumption. And I can derive Q or R just by using OR introduction 2 to 9. Then I can do P or Q or R by using OR introduction 2 to 10. Okay. And then finally, I use my OR elimination rule on this box, and this box. Okay. So I have P or Q or R. From P or Q, I derive P or Q or R. From R, I derive P or Q or R. So I can use the OR elimination on 1, 2 to 8, 9 to 11. Okay, so this was a bit long, but it's just repeated application of the 2 rules.
Sir,
Yeah.
sir, in the boxes 2 to 8, we are getting P or Q or R from P or Q. And,
so yeah, correct. From P or Q, I first assume P, I derive this. I assume Q, I derive this. Then I applied this. So I derive P or Q or R within this assumption.
So phi here is P or Q.
Sorry?
Phi in the elimination.
Yes. Yes. Correct. This P or Q is phi or psi. Phi is P, psi is Q, and chi is P or Q or R. Yeah.
Okay.
And then I started with R. I got this somehow, and now this phi is P or Q, psi is R. From phi I derived this, from psi I derived this, and then I got this. Okay, in the outer thing, the phi is P or Q, but in this internal thing, phi is just P and psi is just Q.
Okay, sir.
Okay, good. Okay, so there's one last example, and then we will stop the class. Please try this out. Okay, so in the interest of time, I'll just start writing the proof. You can continue working on it and then check if it's what you have. So let me P and Q or R is a premise. So let me apply the AND introduction, sorry, AND elimination on one. See, here we also need to use the rule that we had for AND. Okay, if I had phi and psi, I can derive phi, I can also derive psi. So this is the AND elimination one. I can also derive Q or R. This is the AND elimination 2 applied to 1. Now, I have to derive this, okay, and I have only this and this. So what I'll do, I'll try to use the OR elimination. So I'll assume Q, okay. if I assume Q, since I already have P is kind of in the global context, it's true. So I can derive P or Q by the OR introduction applied to 2 and 4. And once again, I can apply the OR introduction. Because in the OR introduction, you can arbitrarily add some formula. If you have derived phi, you can just put phi or psi.
Sir,
yes?
So we need P and Q and P and R.
Sorry. This is what I, sorry. You're right. This is P and Q. So this is the AND introduction rather. AND introduction. Now I apply the OR introduction. So I get P and Q or P and R. I apply the OR introduction to just phi. Because the OR introduction was, if I have phi, I can always derive phi or psi. Okay. I finish this. Then I start an assumption R. Okay. Now I apply AND introduction to 2 and 7 to get, so this is my assumption, to get P and R. And now I apply an OR introduction to get P and Q or P and R. OR introduction to 8. So now I can apply the OR elimination to this thing, this box and this box. This is my phi or psi. From phi, I get chi. From psi, I get this chi. So I can derive chi, which is P and Q or P and R. I apply the OR elimination to 3, 4 to 6, 7 to 9. Okay, so I'll let you take a look at it, in the coming days. So I also have another thing, but I will leave that as an exercise, the converse of this. So from P and Q or P and R, derive P and Q or R. You can just note this down and then try it out. But I'll stop today's lecture. So the more exercises you do, you will get the hang of it. I will try to send some problems, or I'll ask the teaching assistants to send some problems for you to deal with. So what have we seen so far? We have seen this, we have motivated this idea of sequence through some problems. Now we will just look at sequence. And then we want to write proofs of sequence using some certain rules of application. And we saw some rules which dealt with OR and implies. So we have not seen rules that deal with negation yet, because in the original last week, we also had, last class, we also had negation in the formulas. When we had to write, when we derived the sequent from the question, we also had negation. So we need to deal with negation somehow. So we will see some more rules. Okay, I think there'll be some 3 more rules. We will see it next class, and then we have all the rules that we need to prove sequence. Okay, so I'll stop here and then we can continue next class. So if you have questions, you can ask me, but apart from that, the class is over.
So are the rules, are there any proof for the introduction and elimination rules, or they're just axioms or something like that?
So there are proofs to show that they are sound. That is, if you apply this rule, you are not going to do something wrong. Okay. So that you can just look at it by the truth table also. If you have phi, if I have derived phi, I can always derive phi or psi. So if phi is 1, phi or psi will be 1 intuitively.
Yes, correct.
Okay. So that is a soundness. But more tricky is, after I finish the next 3 rules, question is, is it complete? Will I be able to prove any sequent using this set of rules? That is a non-trivial question, and the answer is yes for that also, but we will not see the proof of that. Okay, I just want to give you info. You either take it or leave it. Don't worry about it. Okay? As long as if you're given as for the purposes of this course, you need to know, given a sequent, how to apply these rules and write a proof. Okay, so this is just adding symbols to the way you reason about problems. Okay, so that is this entire point of logic. Okay, yeah. Okay, so if there are no other questions, I'll stop share. Okay, so then we will see in the next class. Okay, see you then. Bye.
Thank you, sir.
Thank you. Yeah.
Thank you, sir. Bye, sir.